The first problem of 2.4 is very easy. In the figure, very simple figure is there. There is one circle, one tangent and two chords. This is A, this is D, this is B, this is Q, and this is P, and this is any angle C. Okay, simple figure. In the figure, segment AB and AD, AB and AD are the chords. Line AC is tangent to the circle at a point A. If major arc APB is 80 degrees, major arc APB, this is 80 degrees, angle BAD is 30 degrees, angle BAD is 30 degrees. Find out angle BAC. BAC, we have to find this angle. Angle BAC we have to find out, and then major arc BQD. This we have to find out. This example in October 12 exam for 3 marks. Extremely simple example, extremely simple. Simple thing, this angle we have to find out. This is the tangent, this is the chord. By tangent secant theorem, this has to be 40 degrees. Okay, and angle major arc BQD, by inscribed angle theorem, it has to be double, that is 60. No doubt, 3 marks in your pocket, simply, extremely easy example. So let us go ahead. Okay, the figure is something like this. AB, this is point A, this is point B. You also draw a rough figure along with me. Okay, you also draw a rough figure. Then D and E. D point is here, E is point here. Okay, let us read the example now. If the chord AB of a circle is parallel to the tangent at C, prove that AC equal to BC. AC equal to BC. This we have to prove. Correct? If we have to prove this, if you can prove that these two angles are same, equal, then this is the isosceles triangle, then opposite sides must be equal. Now, in this case, I will name the angles. P, Q, R and S. I am naming these angles. Now can you see that this angle S, angles in alternate segment, this angle S and this angle Q are same, equal, because angles in alternate segment, S equal to Q. Similarly, this is the common arc, so R equal to P. Correct? But now, can you see that these two lines are parallel, this is transverse, so alternate angles are equal to also Q. And hence, from this and this, I can say if R is equal to P, R is equal to Q, then P is equal to Q. This angle is equal to this angle. And if this angle is there, then in a triangle ABC, the base angles are same. This is isosceles triangles. So the side AC and BC are also equal. Reason for every step you have to give. Now here also I'll suggest first you solve like this by giving the names to angle. Declare it. Let us these angles be PQRS. And then secondly, by second time, you don't give these angles, angle names, and write down the proper names. And now see how complicated it becomes. Okay, so this is very simple. So here we have made use of the angles in the alternate segment, parallel lines also, and inscribed angle theorem also. So this is just a combination of all. Let us go to next example. Problem number 3 of exercise 2.4. The figure is given something like this. We'll read the problem. In a cyclic quadrilateral, if one pair of opposite side is congruent, they are given AD and BC are congruent sides. Okay? Then show that the other pair of opposite sides is parallel. We have to show that DC is parallel to AB. This is what we have to show. Cyclic quadrilateral is given. If this chord is congruent, O is the center. If these two chords are congruent, then their central angle must be congruent, and hence these arcs are also congruent. Okay. Now here, while proving, I am not going to call the arc AD, C and B, C, D, something like that. I'll simply call them as the Y, Z and X. Okay. Now by central angle property, X and Y, arc X and Y are same, equal, X equal to Y. Now I will add this Z to both the sides. Correct? Now I will call this arc X plus Z. This arc, can you see, it is intercepted by ABC, angle ABC. Now I will give names to these angles also. I will give name to this angle as alpha. I'll say this is as a beta, and I'll say this is as a theta. Okay. Now X plus Z, this arc is intercepted by beta. Correct? And Y plus Z, this arc complete is intercepted by theta, and hence theta is equal to beta. So these two base angle of the cyclic quadrilateral are congruent. Correct? But alpha plus beta is equal to 180. Opposite angles of the cyclic quadrilateral are supplementary. So these are 180. So now can I say that instead of this beta, I can write theta from this alpha plus theta is equal to 180. So this angle plus this angle is equal to 180. That is what the taste for the interior angle for the parallel lines. Interior angles are supplementary, and hence DC is parallel to AB. So simple. Correct? Don't go on figure. Don't go on writings of the names of the arcs and the angles. Even if you want to write down that on the rough figure, you can do something like this. This is very simple example. Correct? Let us go ahead. Now we are going to see the fourth example of 2.4. This is the figure they are given. Let us read the problem. Suppose ABC is a triangle inscribed in circle. This is the triangle ABC inscribed in a circle. The bisector of angle ABC intersect the circle in point D. Now angle bisector of this B intersects the circle in D. The tangent at D intersect line AB and BC in E and F. This is the tangent, and it intersects these two arms or lines in E and F. We have to prove that angle EDA is equal to FDC. EDA, this angle, is equal to this angle. That is what we have to show. Let us call this as the alpha and beta. Okay, and let us call these angle as P and Q. Okay, this problem is extremely simple, only the figure is unnecessarily complicated. Now here we have to just use one theorem 2 times, that is angles in alternate segment. Forget about this. This is tangent, this is chord, so this arc is intercepted. So this angle theta and angle P are same because same arcs are intercepted. Right? Angles in the same arc. This is called as tangent secant theorem. Tangent secant theorem and angles in alternate segment. So here I can say that alpha is equal to P, and same in this case, this is the arc is intercepted by this angle Q and also by the angles in alternate segment, this Q and beta is equal to beta, and hence alpha is equal to beta. Simple, extremely simple example when you call these angles as alpha, beta, P and Q. Otherwise you can even write that angle EDA is equal to angle ABD, and angle FDC is equal to angle DBC, and hence this angle equal to this angle. Proved. Just keep in mind, here you are written alpha is equal to beta, but this is not asked. Alpha and beta, they are not given alpha and beta. First of all, you have to declare it, or at last you have to see, hence angle this is equal to angle this. Whatever is asked should be the final answer. Okay, so keep that in your mind. Now let us go ahead to fifth example. In the figure given, suppose two circles are touching at A. At this point, these two circles are touching. Through A, two lines are drawn intersecting one circle in P and Q. Intersecting these two lines are drawn. It is intersecting this circle with center M with P and Q, and with center N, circle with center N in X and Y. Prove that PQ is parallel to XY. We have to prove that this PQ is parallel to XY. Extremely simple example. If you have to prove, now forget about all these things. If you want to prove the two lines are parallel, then how will you prove? Alternate angles are equal, or interior angles are addition is 180, something like that. So here is the transverse. If you can prove that this angle is equal to this angle, or you can prove that this angle is equal to this angle, either of the pair, then it can be easily proved that these two lines are parallel. Correct? I am going in the reverse way. First of all, I am deciding what I have to do. I have to prove these two angles are equal. Now let us see. I will give names to these angles. Okay, I will call these as alpha, I will call it as a beta. If I can show the alpha is equal to beta, then everything is simple. Now in this circle, angles in alternate segment theta and alpha are same. Theta is equal to alpha. Correct? And now in this circle, can you see that these are the crossing lines and these are the exactly opposite angles theta. This is also theta because opposite angles are congruent, right? So if this is the tangent, this is the secant, and so angles in alternate segment, that is theta is equal to beta. Correct? So from these two, I can say that alpha is equal to beta, and hence I can say that line PQ is parallel to line XY by alternate angle test of parallel lines. Extremely simple example, but here you have to keep in mind that they have not stated that these two circles are touching externally. Okay, they just said that suppose two circles are touching at A. That means this is only one condition where these circles are touching externally, but there is a possibility that circles are touching internally. So let us see the second case here. So what will be the second case? Second case is these two circles are touching internally. Don't look at my figure. My figure is not looking like perfect circle because I have drawn it by hand. You have to draw these figures by pro circle or by angle or something else. Okay. So this is the second case. These circles are touching internally because they are not stated that those circles are touching externally. So we have to consider both the cases. Now you have to keep in mind, this is what I say, read example carefully. If this example is for 4 marks, 5 marks, let us say 4 marks, and if you draw only external, see, because what happens whenever we read that the circles are touching, by general common sense, the common rule, we think that those circles are touching externally, because touch as such is also always external in our mind. Okay, so we always think that. I have seen the papers of many students, they only solve one part of it, that is circles are touching externally. They don't solve the second part and then they lose half of the marks. Okay, so read example carefully, what is given. Okay, so here is the case. Now suppose I want to prove that these two lines are parallel, then what I can use, which test I can use of parallel lines? Corresponding angles. I can prove that these two angles are corresponding angles. Corresponding angles are equal. So in the smaller circle, this angle I'll say alpha, and this I will say beta and theta. This I'll say as alpha. Okay. Now in smaller circle, angle alpha is equal to angle beta. Alpha is equal to beta in smaller circle. And now forget about small circle. In the bigger circle, again this angle alpha is equal to this angle theta. And hence my angle theta is equal to angle beta. Corresponding angle test for parallel lines. And so the PQ and XY are lines parallel to each other. Remember, you have to solve these both examples. Both examples means both the conditions. First condition, circles touching externally. Second condition, circles are touching internally. Only then you will get full marks. Otherwise, no. Sorry. Okay. So you have to just keep that in mind. Read problem carefully. Okay. Let us solve example number 6. This is the figure given. In the figure, points B and C lie on the tangent to the circle. Point B and C lie on the tangent to the circle. This is the tangent line to the circle. Drawn at point A. The tangent is at point A. Chord AD equal to chord ED. Chord AD. Where is chord AD? Yeah. Chord AD equal to chord ED. Major arc EPF is equal to half of major arc AQD. EPF is half of AQD. So I will just write it here. P is equal to half of Q. Okay. I'll just write. I am not going to write the EPF and AQD because all the names of the arcs are given. P, R, Q and S. All these names are given. So I am not writing that. Then they are given major arc DRE is 84 degrees. Major arc DRE is 84 degrees. Now let us see what we have to find out. Many things again, 4 things. Angle DAC. Angle DAC, this angle we have to find out. Then we have to find out angle FDA. FDA, this angle we have to find out. Angle FED. FED, this angle we have to find out. And then angle BAF. BAF, this angle we have to find out. Very simple, isn't it? Let us see what we know about this. Since these two chords are same, congruent side, so the arcs also must be same. So this is 84 degrees. Simple. If this is 84 degrees, then this angle must be half of 84, tangent secant theorem. So this is equal to 42 degrees. Now one more information they are given here. P is equal to half of Q. This P is equal to half of Q. That means this is also 42. Now in the complete circle, we know 42, 84, 84, only S is unknown. And addition of all the things are 360. So I can say that P plus, instead of letters direct write down the values, I can say that 42 plus 84 plus 84 plus S is equal to 360. So what is S is equal to? Find out quickly, pause your video here. So S is 150 degrees. If S, this arc is 150 degree, now what we want? Which angle? Now this is tangent, this is chord, so this angle must be half of 150. Correct? Tangent secant theorem. So this is 75 degrees. Now this angle is intercept which arc? S plus Q. So 150 plus 84 is this angle. What is 150 plus 84? So this angle I am not calculating, 150 plus 84, I am just writing it here. Now this angle is intercepting this arc, that is arc S. So if this is 150, this must be 75. Problem solved. Minimum 3 marks, 3 to 4 marks you will get in this problem. This you can find out by some other method also, like if this is 75, this is 42, so this angle you can subtract 75 and 42, you will get this angle. Then these two angles are supplementary, cyclic quadrilateral. So by that way also you can find out these two angles, doesn't matter, but they are asked here, na, 150, that is why we found out this. Just to remind you, before going to next example, here I have written 150 plus 84. It is not 150 plus 84, it is divided by 2. Don't make mistake. I just told you orally, because this angle is intercepting arc of 150 plus 84. And by inscribed angle theorem, it should be half of that. I have written 150 plus 84 because it happens in one of my class. I just written so that, because that was the last value. I just written 150 plus 84, so you can find out the angle. And student just added the things. 234. No, that will be equal to 117. Half of that. Correct? Inscribed angle theorem. Don't forget that. So let us now go to next example. Let us go for the 7th example. Cyclic quadrilateral ABCD is given. Let us draw one cyclic quadrilateral. It is extended here. ABCD. ABCD. Don't look at my figures. Draw your own figures. Okay. And then this extension is E here. Let us read the problem. ABCD is a cyclic quadrilateral. Major arc ABC is 220 degrees. ABC is, this is 220 degrees. ABC 220 degrees. Find angle ABC. What to be find out? ABC. Angle ABC. This angle. Then angle CDA. This angle. Then angle CBE. CBE. This angle. Since ABC is 220 degrees, this angle must be half of that, that is 110 degrees. Since this is a cyclic quadrilateral, this angle must be 70 degrees. If this is 70, this must be 110 degrees. An example is over. Extremely simple example. Okay, don't even expect this example to come in exam. Okay, but you have to write that the opposite internal angles of the cyclic quadrilateral addition is 180. That is, those angles are supplementary, and so on. Okay, let us go to next example. So every time I am solving the example, I am just telling you orally that this is the inscribed angle theorem and all these things. I am explaining you the example in a very, very simple way. But when you are writing it, you have to write the full example along with the reasons, along with the statement, reason and all. I don't have to explain you that how to write the statements for the problems, okay, that you are going to learn in your school, in your classes, in your books, everywhere it is there. But as a natural law, if I want to write something, I will use the natural law. That means whatever I am doing, I am writing it and I am just writing in front of it why I had done this. Or first give the reason, then say hence it is like this. Okay? There is no specific rules and regulations over there. It's not like that one student has written 7 steps and another student has written 8 steps, so he'll get 1 mark more. No, it is not like that. Only examiner should know that you have written it properly and you know what you are doing. You are given the reasons to each and every step. Correct? So this is what the important is. So let us go to next example. So let us see now example number 8. This is the figure. It is in the blue, not because it is so special kind of example. It is blue because I have not used blue pen for a long time. Okay. So this is example number 8. Let us read the example. Let M be the point of contact of 2 internally touching circles. These 2 circles are internally touching, bigger circle, smaller circle. M is the point of contact. Let line AMB be their common tangent. This line is their common tangent for both the circles. The chord CD of the bigger circle touches, CD touches the smaller circle. Chord CM and DM, chord CM and DM are of the bigger circle. Prove that CMN, let us mark it out, CMN, this angle is equal to DMN. DMN is equal to this angle. We have to prove this. Now, how will you proceed? Just I have to add one thing, one construction here. Since here it is tangent and lot of chords are there, but for this tangent there is no chord, so I'll just draw one chord here, that is NR. Okay, this chord I am drawing here. I am joining this NR. Okay, now let us see what we know about this. Okay, now first of all, if I am considering the bigger circle, then this is the tangent, M, this line is a tangent, this is secant, and so alternate angle in the same segment. So this angle, I will call this as angle alpha. Okay, this angle is equal to angle beta here. Correct? Now this is tangent, this is secant, so I can say that this angle is equal to this angle. I'll call this angle as theta. Here instead of beta, I will straight away write alpha and alpha. Correct? Because both the angles are same angle. So this angle alpha is equal to this angle alpha. Now in this smaller circle, if this N, R and M, this big arc, if this is arc, then this is tangent and this is chord. So this big arc, this MPN, this big arc is intercepted by 2 angles. One is the NRM and with this tangent and this chord. So now I will call this angle as X, suppose. Okay. So this complete angle, that is alpha plus X, these 2 angles combining is equal to this angle QRM, because angles in alternate segment. Again I am telling you, forget about the bigger circle. In smaller circle it is something like this. In smaller circle it is something like this. That figure is something like this. This complete. Whereas there are 2 things, so this plus this. Okay, so that figure is little bit complicated, so I have shown it on the smaller scale figure here. So what will be this angle equal to? This angle is equal to alpha plus X, this bigger angle. So this is equal to alpha plus X. Correct? This angle equal to alpha plus X. Correct? Now if you consider this triangle NDR, this alpha plus x is an exterior angle, correct? So it is equal to addition of two remote interior angles, that is theta plus alpha. Now alpha is common, so x is equal to theta. So here also x is equal to theta, which we have to prove. Again I am explaining you, I know this is quite complicated example, but here our old reverse engineering method applies. First of all, write down whatever you can understand from this figure, that's all. So I know this is in this angles in alternate segment is going to be used, inscribed angles theorem is going to be used. So first of all I will say that I'll go from outside to inside. So for external circle, CMA is alpha, which will be equal to this D alpha. So this is alpha and this is alpha. These two angles are congruent because angles in alternate segment. Now if I go inside for the inner circle, if this is angle theta, then this is tangent, this is theta, so this is also angle theta. So these two are angle theta. At this point also nothing is in my mind how I am going to solve this. I am just writing what I know from this or what I can find out from this figure. Then I want this, but this is not possible. So I am taking this hole in a smaller circle. I can say that I have joined this NR. So NRM is this bigger arc which is intercepted by this AM and N. Correct? So my alpha plus x, this bigger angle, is equal to this NRM. So I have written alpha and x are there, so I have written addition here. Here I have not written addition because both the angles are separate, I can see there. Now this much information I can get from this. Now what? Now I can say that this is looking like a triangle. This is a triangle and this is the external angle. Correct? So I have written this external angle is equal to the addition of remote interior angles. So when I write this alpha gets cancelled and ultimately I got x is equal to theta, which is nothing but x and theta. So it is proved. So here you can say, but x plus theta are these angles, name the angles, and so it is proved. I could have explained you with the name of the angles, but I am not doing that because I know if I go on taking the names of the angle 1, 2, 3, 4, 5 and 6 names, you are definitely going to confuse. So for explanation, simple explanation, I am taking the angle names here. Okay. So let us go ahead. This was not very simple example, little bit complicated example. Let us go ahead to next example. So this is ninth example of 2.4. There are two intersecting circles are there which are intersecting at A and B, and CD is the common tangent to them, and we have to prove that CAD plus CBD is 180 degrees. CAD this plus this, these two angles are equal to, addition is 180 degrees. Now how will you solve this? Let us first understand what we know. Suppose I call this angle theta, x, alpha and beta. Okay, different angles. So in this circle, smaller circle, can you see that this arc is common for angle alpha and theta both? So by angles in alternate segment, this theta and alpha are same. So I will better call this angle also alpha. Correct? Similarly, in this circle, this arc BD is common for angle beta and angle x. So I will call this also angle beta. Correct? Now can you see this alpha and beta is nothing but angle A. We have to prove that angle A plus angle B. Here I just call it as a common angle A and angle B. So in this small triangle, can you see that alpha plus beta plus angle B is equal to 180. right? But alpha plus beta is equal to angle A. So angle A plus angle B is equal to 180, and it is proved. Very simple. Once you give the names to such angles, these calculations and problem becomes very simple. But here again you have to first state that let us this be angle A, or first of all you say that by the angles in alternate theorem, angle DCB and angle CAB are congruent, are same. So let us call them alpha and write them alpha. Similarly, in bigger circle, let us call these angles beta. Now in triangle CBD, the addition of all the angles is 180 degrees. So alpha plus beta plus angle CBD, instead of B you can write CBD, angle CBD is equal to 180 degrees. But alpha plus beta is nothing but, here also alpha plus beta nothing but angle CAD. So I have written angle CAD, and hence angle CAD plus angle CBD is equal to 180 degrees, and that is proved. Simple example, let us go ahead. This is the last problem of 2.4. Let us read the problem. Let the circles with the centers P and Q touch each other externally. Now they are given externally at a point A. Let the extended chord BA intersect the circle with the center P in the point E. This chord, extended chord, intersect here. Chord BC touches the circle. Chord BC, this second chord is touching this circle at point D. Okay. Prove that ray AD is the angle bisector of CAE. CAE, this angle is equal to this angle. That we have to prove. Okay. Not very difficult example. What I have done, since both are the touching circles, I have drawn one tangent, common tangent to this, and I have joined ED because I want to use the angles in alternate segment theorem. Okay. So now this is the tangent, and can you see that this angle and this angle are same because angles in alternate segment? So can I write the alpha and alpha here? Both the angles are same, correct? Now this angle, this arc is common, so this angle is beta and this is also beta. So this angle EDS is equal to angle EAD. So I have given name both of them alpha because angles in alternate segment. What else I know here? Now let us, this is tangent and this is chord. So this angle up to here, this angle and this angle is same because angle in alternate segment. Can I call them as X and Y? So this is X, so this is also X. And similarly, this is the tangent and this is the chord. So this arc is common. So alternate angles in alternate segment, can I call this angle as Y, and which is equal to this angle? Correct? Because the arc is common. Alternate angles in alternate segment. Now in this bigger triangle E, B and D, this alpha is the external angle. This external angle is equal to the addition of remote interior angles, that is X plus Y. But these two angles are also X plus Y. So these two angles X plus Y, now I can give the name. Okay, this is angle alpha. So angle alpha EAD, angle EAD, and this X plus Y I can give name DAC, angle DAC. So since angle DAC and EAD are equal, that means this AD is the angle bisector of CAE. It is as simple. Have you understood this problem? They have asked that angle, that AD is, this line AD is bisector of CAE. So my first step was, this is the angle alpha which is equal to this angle, because angles in alternate segment. Next I saw that I took this as a tangent, so my this smaller angle x is equal to x, and for this circle this y is equal to this y. Okay, correct? Now I have taken this bigger triangle. In this bigger triangle, this angle alpha is the exterior angle, so it is equal to the remote interior angle addition. So this is equal to x plus y. So my alpha is nothing but EAD, and my x plus y are here also. X and y are here also. So x plus y are nothing but DAC. So my EAD equal to DAC, and hence AD is angle bisector of the angle CAE, which is proved. Correct? Or in other words, you can write that, so angle alpha is nothing but x plus y. So in this way we have proved this problem, which was the last problem of exercise 2.4. Problem was not very difficult, but you have to understand in what sequence you have to take. My suggestion is always analyze the figure first, just jot down roughly on the figure whatever you know about it. So automatically the problem will get solved. See, the problem in writing the names of the angle is, now here in one shot, in one view you can understand which angle is congruent to which angle. But here you cannot, if you write the EPD and EDS, you will not understand which angles are congruent to which angles. Correct? So here you can say this is x plus y is equal to alpha. That is what you want to prove. X plus y is equal to alpha you want to prove. But what is x plus y? X plus y is this. This is also x plus y. And what I can say about it? Oh yeah, this is the exterior angle. So this is the advantage of writing the names, giving the names to angles. In one view you understand the problem perfectly. Okay, but as far as possible write the names properly, or you declare the angles. Let us take the name. In one sentence you write, let us give the names to angle x, y, z and so alpha, beta, gamma, something like that. Okay, and then solve this. So with this problem here we finish exercise 2.4. Thank you very much. Now we'll go for last topic, then exercise 2.5, and then the problem set of this chapter, circle. Thank you very much.